We'll start now.
I think better we start now.
Yes, we'll do that. Yogesh sir, how many more in the waiting room?
50 are showing right now. I am admitting them.
Okay, I'll start now.
Yeah.
Uh, Monish, can everybody hear me?
Yes, ma'am, we can hear you.
Yes, you are
All the
quite audible.
participants. Okay. Without wasting much time, we start the session now. Good afternoon to one and all. I'm Mrs. Vedika Dadlani. On behalf of Dr. L.H. Hiranandani College of Pharmacy, would like to welcome you all for this two-day national webinar on GCMS and AAS from basics to applications, organized in collaboration with Toshwin Analytical Private Limited. In these 2 days, our speakers, Mr. R. Girijan and Mr. Mata Prasad Saroj, will introduce you to the basics, theory, instrumentation, and advanced applications of GCMS and AAS, and also highlight the emergent trends in the same. With this small note, I welcome our first speaker for today, Mr. R. Girijan. I would like to share something about Mr. R. Girijan. Mr. R. Girijan is a product consultant in the field of analytical instrumentation with around 42 years of experience in the analytical field. He is a postgraduate in analytical chemistry, fellow of the Institution of Chemists India. He is a member of the American Chemical Society and is also a life member of Indian Society of Industrial Chemistry. He has worked in pharmaceutical as well as paints and polymer fields and has approval from FDA Maharashtra in the field of chemical and instrumentation analysis. He has extensive experience in chromatographic and spectroscopic analysis. He is a guest lecturer at various institutions of national repute, corporates, as well as universities and colleges. He has undergone advanced training in the field of chromatography and spectroscopy at Thermo Fisher Scientific UK and Italy, and also at Shimadzu Corporation, Japan, China, and Singapore. Currently, Mr. R. Girijan is working with Toshwin Analytical Private Limited, Mumbai as a product consultant. With this small introduction, we welcome Mr. R. Girijan for his first talk.
Thank you, Vedika, for the wonderful introduction. I am too happy to be associated with this webinar today and tomorrow on two important analytical techniques. One is gas chromatography coupled with mass spectrometry and atomic absorption spectrophotometry, which is going to be tomorrow's topic. Am I audible to everyone? Am I audible?
Yes, sir.
Yeah. So I really appreciate the initiative taken by LH Hiranandani College of Pharmacy for organizing this two-day webinar on two different analytical techniques. We are all in a very difficult situation. We are all locked inside because of the current situation. And this is the best way we can utilize the time available to all of us. And these type of programs are going to be very, very beneficial, especially for the student community. And that is, I mean, they are going to be the biggest beneficiary. So let us start with today's topic, which is a very, very important. All of you will agree with me. It's a very important analytical technique. Chromatography is all about separations. I hope everyone knows about it. Chromatography is all about separations. Because when we talk about analytical techniques, they can be classified into three different classes. Number one is separation techniques. Second one is identification techniques. And the third one is material characterization techniques. And each one has got its own members. And each class is important by itself. So under separation mechanisms, we have different types of techniques available, like gas chromatography, we have liquid chromatography, we have ion chromatography, we have supercritical fluid chromatography. There is a long list of members coming in this family. Similarly, and the other two classes also, identification as well as material characterization. So today, chromatography has become a very, very important part in our life. I mean, we have come to a stage today that without chromatography, we just cannot exist. I mean, it has come. I mean, that is the importance that chromatography assumes today. If you whatever field you are talking about, like life science, pharmaceutical field, polymer field, food chemistry, perfumery industry, flavoring industry, environmental analysis, whatever field you are talking about, we have got wonderful applications of chromatography. So chromatography is essentially it is a separation mechanism. It's basically a physical separation method. Why we specifically say it's a physical separation method? In any chromatography process, there is no chemical reaction taking place. Only physical interactions are there. So any chromatography process will involve only physical interactions and no chemical reaction. So that is specifically, that's the reason why we specifically say it's a physical separation method. It involves the distribution of components between two phases. That's a very basic requirement for a chromatography process to take place. For any chromatography process to take place, the minimum requirement is it should have two different phases. One is called a stationary phase, and the other one is called a mobile phase. And without these two phases, a mobile phase and a stationary phase, no chromatography process can take place. So that's a basic requirement. And when you're having a sample, you are having a sample which contains more than a compound. It can be 2 compounds, it can be 3 compounds, it can be even 100 compounds, even more than that also. So when you are having more than a compound in your sample, and when this sample is introduced into a chromatography system which contains a stationary phase and a mobile phase, these compounds in your sample are going to be distributed between these two phases, stationary phase and mobile phase. Now, if you look at the slide, again, stationary phase there are two different types of stationary phase are available in gas chromatography. One is a solid material and one is a liquid material. And against solid, I have put roughly can be either a solid material or a liquid. And when I say solid 10% and liquid 90% means if I have got 100 applications in GC, if I am getting 100 applications in GC, out of these 100 applications, 90 applications can be successfully carried out with a liquid stationary phase, and the remaining 10 applications can be carried out with the help of a solid stationary. This is a very, very approximate what we call distinction. So that simply means liquid stationary phases are more versatile, more used, more useful, and the solid stationary phases has got a certain specific segment. Especially when we talk about gas analysis, different types of gas analysis. It can be very complex hydrocarbon separation. It can be natural gas separation. It can be refinery gas separation. It can be noble gas separation. Different types of gas analysis. We normally prefer a solid stationary phase because a solid stationary phase can give wonderful separations for even very complex gas samples. So it is actually catering to a certain specific segment. That is the reason why it is assigned about 10% of weightage. Whereas the rest of the segments you talk about pharmaceutical analysis, you talk about analysis pertaining to food chemistry, environmental analysis, polymer analysis, perfumery analysis, whatever it is, we prefer a liquid stationary phase. So it is more versatile and it is widely utilized. And in the case of GC, your mobile phase is going to be gas, and that is the reason why we call it as gas chromatography. Okay, so everyone knows about it. And depending upon the mobile phase and the stationary phase, Chromatography can be divided into various types. So you are seeing different columns. In the first column, we'll see what is the type of mobile phase we are going to use. And the second column, you'll see what is the type of stationary phase we are going to use. And the third column, you'll see what is the principle of separation. And what is the last one, we'll see what is the technique. The first column, I'm going to use a gas as the mobile phase. My stationary phase is going to be a solid material. My principle is based on, the separation principle is based on adsorption technology. And the technique is named as gas solid chromatography. And this is the technique we always refer to when we have a gas analysis. Normally for gas analysis, we always utilize a GSC technique. Now again, I have a mobile phase, which is a gas. But now the stationary phase is going to be a liquid. Then the principle is partition. The separation is taking place on the basis of partition technology. And the technique will be named as GLC, gas liquid chromatography. So under gas chromatography, we have two different types. One is called gas solid chromatography and one is called gas liquid chromatography. The difference is only in the type of stationary phase. One has a solid, another one has a liquid as the stationary phase. The rest of the things are all same. Instrumentation is all same, everything is same. Detection technology, everything is same. We are coming to liquid phase. We are going to use a liquid as the mobile phase. Again, we have a solid stationary phase, and adsorption is going to be the same technology. For that is principle, and the technique is going to be LSC, liquid solid chromatography. Like your GSE, it is going to be LSC. And again, we can use a liquid mobile phase, and stationary phase now is going to be a liquid, and the principle is like your GLC, it is going to be partition, and the technique is going to be LLC. Liquid chromatography. Like your gas liquid chromatography, we have liquid chromatography, which is more versatile, more widely used. Here also it is more widely used. Then we can have a liquid as the mobile phase. Our stationary phase can be a porous polymeric material having well-defined pore size in terms of angstrom unit. A well-defined porous material that can be used. Many times it can be a copolymer also. I mean, it's a polymeric material, porous polymeric material. Then the principle of separation is based on exclusion, size exclusion, and the technique is known as SEC or GPC, gel permeation chromatography or size exclusion chromatography. A technique is widely used in polymer industry for characterizing different types of polymers. It is you can consider it as a part of liquid chromatography, but the column type is different. The separation mechanism is different. Everything is different. So it is considered as a technique by itself, SEC or GPC, gel permeation chromatography or size exclusion chromatography. We are going to use a mobile phase as a liquid as the mobile phase. We are going to use a ion exchange resin as the stationary phase. Then the principle of separation is based on ion exchange. It can be both cation exchange as well as anion exchange. And the technique is known as IEC, ion exchange chromatography. So there are two different techniques, IEC and IC. Of course, that is not the scope of our discussion today. IC and IEC. IEC is called ion exchange chromatography, and IEC is only ion chromatography. That's a difference between these two also, but I'm not going into those details. Then we can use a liquid as the mobile phase, and then the stationary phase is going to be a very thin plate, either a metallic plate like an aluminum plate or a thin plate of glass, coated with a uniform layer of silica. And everyone knows silica is a highly adsorbent material, and the principle of separation is based on adsorption technology. And the technique is, every student will know this TLC, thin layer chromatography, which is a very, very primary analytical technique in the field of chromatography. It's a very quick screening technique even for a difficult sample. TLC. Now TLC has become more automated. Now we talk about the HPTLC, which is a much advanced technique, HPTLC. But TLC is still being followed by many people. It's a useful technique for a quick screening of a given sample. So these are various types of chromatographies which are classified on the basis of the type of stationary phase and the type of mobile phase. Okay, now specifically when we talk about GC, and whatever you see on this slide, these are all in comparison with liquid chromatography. My GC analysis time is always shorter, so you say a short analysis time. Normally, everyone knows people who are experienced on LC analysis time takes analysis time will be much longer compared to GC. Lot of reasons also for that. Wide choice of stationary phases. We have plenty of stationary phases in the case of GC. The moment I say GC stationary phase, I am referring to the column, because today when we have a chromatographic analysis, we have to select the right type of column, HPLC column or a GC column. And the moment I say column, I am referring to the stationary phase, because stationary phase is contained inside the column material. Column. Wide choice of detectors. We have different types of detectors available for different types of applications. And GC is comparatively a very easy technique. Even the operation is also quite simple and easy. It's a very easy operation. And what are the goals of carrying out a GC analysis? To separate mixtures of organic compounds. Sometimes this can be a little misleading. You may think why only GC can be used for organic compounds. But even before we discuss this slide, you also should understand what are the limitations of GC. Every analytical technique, that's a universal rule. Every analytical techniques may be having a lot of advantages. At the same time, they also may be having a set of limitations also. So GC also has the certain limitations. The limitations for GC are mainly two. One is it is applicable only for volatile samples. If the sample is totally non-volatile, GC cannot be directly applied. So that is a major limitation for GC. It can be applied for only volatile samples. By volatile samples, I mean samples that can be converted into vapor form by heating. Okay, so that volatility is one of the major constraints when we talk about GC. So it's applicable for volatile samples, number one. Number two, it is also applicable for thermally stable compounds. That means thermal stability of the compound will come into picture. Thermally stable means when I am heating the sample, because I need to convert the sample into vapor in the case of GC. That is not required in the case of LC. But in the case of GC, we are going to heat the sample and we are going to convert the sample into vapor form. And there are certain samples which when we are heating them, they will go to vapor form. But during the course of vaporization, they will also undergo some decomposition. That means the compound will get disintegrated when the sample is getting heated. That means they are thermally unstable samples. They are known as thermolabile samples. For those type of samples also, GC is a major problem. So GC has got these two limitations. So for any sample to be analyzed by GC, the sample has to be volatile, number one, and the sample has to be thermally stable also. Unless these two conditions are satisfied, the sample cannot be analyzed by GC. Then LC may be the answer for that. Okay, now in that context, when we talk about inorganic compounds, most of the inorganic compounds are totally non-volatile from the GC perspective. That is the reason why we are not able to analyze most of the inorganic compounds, inorganic oxides, inorganic salts, inorganic chelates, and all those. They're out of question as far as GC is concerned. But still we can use GC for certain samples, inorganic samples, but those samples are always in the gaseous form. Think of gas analysis. Even simple atmospheric air, the composition is approximately 21% nitrogen and 79% nitrogen and 21% oxygen. We can separate these two by a column at room temperature using a GC. You will get two beautiful peaks corresponding to nitrogen and oxygen. It is an inorganic separation, but the compounds are already in the gaseous, so they are already gas samples. So there is no problem. So we can separate it. We can use GC for the separation of carbon monoxide and carbon dioxide, an extremely critical application in petrochemical industry and fertilizer industry. Carbon monoxide, carbon dioxide content in the incoming gas streams. Very, very critically to be monitored. And we do it by GC. Again, it's an inorganic separation, but carbon monoxide and carbon dioxide are already gas samples. I can separate oxides of nitrogen. We can separate oxides of sulfur. and ammonia. I mean, these are all inorganic compounds, but they are all gaseous samples. That is the reason we are able to separate those compounds. But barring these very few compounds, most of the remaining inorganic compounds cannot be separated by GC because they are totally non-volatile. Okay. Whereas in the case of organic compounds, most of the low molecular weight organic compounds are volatile. So here also you have to keep in mind there is a molecular weight cutoff. Any sample whose molecular weight is more than 600 normally becomes non-volatile. That is the reason why when we talk about peptides and high molecular weight compounds, and we don't use because we don't use GC because GC cannot be used because those compounds become totally non-volatile because of high molecular weight. We talk in terms of 3000 Dalton, 4000 Dalton, 5000 Dalton molecular weight for those proteins and peptides and all because they have to be analyzed only by GC. Only by LC. So any organic compound which has got a maximum molecular weight range up to around 600, and they are collectively called small molecules, they can be analyzed by GC because most of them are volatile in nature. So that is why GC is used for analysis of small molecule compounds which has got a maximum molecular weight of approximately 600. To detect individual analyte, to identify and quantify using reference standards. In the case of GC as well as HPLC, once you get a separation, you have to use a reference standard to identify what is the separated compound, and subsequently if you want to quantify that, there also you require a reference standard. Because in analytical chemistry, the moment you say quantification, you require standards because we have to create a calibration curve. And without creating a calibration curve, quantitative analysis is not possible. And to create a calibration curve, you have to have reference standards. It is a absolute requirement for any type of analysis, whether it is chromatography analysis or spectroscopy analysis. That is the requirement. So you should have standards with you. Okay. A GC is comprised of, for the students' benefit, I'm slightly explaining about GC. I'm not going into details. Then I am coming to the mass spectrometry side. A GC is comprised of mainly 5 different parts. One is a flow controller. Then we have an injection port. We have a column which is always present inside an oven. Then we have a detector. And finally, the data processor, nothing but the software and PC. Flow controller is required because your carrier gas mobile phase is going to be a gas. We call it as a carrier gas, and that is present in a pressurized cylinder. That's the source of your carrier gas. The cylinder is always at a very high pressure. A full cylinder pressure can vary from 140 to 160 kilograms per square centimeter. Whereas the pressure that is required on the equipment is approximately 6 to 7 kilograms per square centimeter. So we need to control the pressure that is coming to the equipment. So we have a flow controller which will regulate the flow of gas from the cylinder to the equipment. And then when injection port which is heated, injection port is to be heated from different types of samples will require different injection port temperature. The user has to optimize it. Then we have a column which is always present inside an oven, and the oven is heated. That means your column is heated. That is also independently heated. You have to set and optimize the conditions, the temperature conditions of the oven. That is the column. Then we have a detector. Whatever is coming out of the column, it is going to come out to the detector. Detector is also to be heated independently. So in the case of GC, we have 3 different independent heating zones. One is the injection side, one is the column which is present inside an oven, and the third one is detector. All 3 are separately heated by independent heaters. And the detector is going to give out a signal, which is always an electrical signal, and that will be processed by your data processor. And what is the mechanism of zone migration? This slide shows the mechanism of zone migration. It's a very common slide for any type of chromatography. You talk about GC separation, you talk about LC separation, any type of separation. The separation is taking place on the basis of zone migration. What does it mean? I'll just read out what is written. Chromatography separation is due to the differential migration rate of components in the mixture, and the mobile phase helps to move the sample to the stationary phase. What does it mean? I'll make it very simple in a very few this thing, couple 1 or 2 minutes. Suppose you imagine you have a sample which contains two different compounds. Compound A and compound B. It could be a pharmaceutical sample. It could be a normal chemical sample. Two different compounds are mixed in your sample A and B. Now you are going to separate this sample by a suitable chromatography system. It can be GC system or it can be LC system, whatever it is. Now you are going to introduce the sample into the chromatography system, and the moment you introduce the sample, it goes inside the column. From the injection port, when you are injecting the sample into injection port, the sample from the injection port is going to enter the column. And everywhere, in GC also it happens, LC also it happens. Entering the column. And the column contains the stationary phase, and the mobile phase is continuously flowing through the column. In the case of GC, a gas is flowing. In the case of LC, a liquid is flowing. But whatever is the case, the mobile phase is continuously flowing through the column. And the sample has entered the column. Sample contains two different chemical compounds A and B. And the column contains the stationary phase, which is also nothing but a chemical compound. Your stationary phase is also a typical chemical compound. There are certain requirements for a chemical compound to be used as a stationary phase. Okay, so that ultimately imagine that's also a chemical compound, which is a stationary phase, which is present inside the column. Now, when this sample goes inside, which contains two different compounds, these two compounds will be interacting with the stationary phase inside the column. There will be physical interactions, no chemical reaction, only physical interactions are there. Now, assume that the stationary phase inside the column likes the compound A in your sample, whereas it doesn't like the compound B in your sample. That means there is a certain affinity, degree of liking between compound A and compound B. There is a high degree of affinity between compound A and stationary phase, whereas the second compound's affinity is bare minimum. It doesn't like the stationary phase. So in that case, what will happen? The one which has got a higher degree of affinity toward the stationary phase will try to remain inside the column for a longer period of time, whereas the one which has got least affinity toward the stationary phase will try to move faster and try to come out of the column. And the one which has got maximum affinity, that also has to come out. It cannot remain permanently inside the column. It also has to come out, but it will be moving slowly because it has got a higher affinity. It would like to remain as much time as possible inside the column, but that also will be moving, but it will be moving at a slow rate. So that means you imagine two different compounds having two different degree of affinity toward the stationary phase, which is present inside the column. These two compounds will be moving at two different rates. The one which has got minimum affinity will move faster. The one which has got maximum affinity will move slower. That means their migration rates are different. They are moving at two different speeds. Migration rates are different. And it is the difference in this migration rate of these two compounds which has ultimately resulted in their separation. That means the one compound B has least affinity, it will come out of the column fast, and that will be detected as the first peak by detector. And after some time, the first compound, that is compound A, will come out, but then that also will be detected as the second compound. So, but A will come out later and B will come out early. They are well separated. There can be minutes of difference between the retention time. The first one has come out after 5 minutes. The second one has come out after 10 minutes, like that. Now, when you talk about a binary sample, that means a sample which contains only two different compounds. This process of optimization is very, very simple for you. But today, when I talk about a multi-component system, a perfumery sample, multi-component pesticide residue samples in food products, or a naturally occurring medicinal oil, or a very complex hydrocarbons, there can be more than 100 or much more than number of compounds in a given single sample. So that means your sample contains 100 different compounds or more than that. all these 100 different compounds should move to the column at 100 different speeds. Then only all the 100 compounds can be separated. Otherwise, if two compounds are moving together, they will come together without being separated. In the chromatography parlor, we call it as a coelution. That's a problem for us. So that means selection of column becomes very, very critical. Today, we have very, very high resolution, very long length, high resolution capillary columns available, which can separate even the most difficult multi-component naturally occurring samples. That is the state the chromatography has come to today. Over a period of the birth of chromatography was in the year 1905, and today we are in 2020. So almost over a period of more than 100 years, the chromatography has developed into a very, very advanced technology, which has the capability to separate even the most complex sample available. Okay, now let us go to the next slide. General chromatographic equation. Distribution of a component X between the stationary phase S and the mobile phase M. You are introducing a sample, your sample molecule X is the sample molecule. When it goes inside a chromatography system, there is a stationary phase which is denoted as S and mobile phase denoted as M. The compound, your molecule, is going to be partitioned or distributed between these two phases, mobile phase as well as stationary phase. See that equation, very simple equation. XM is in a dynamic equilibrium with XS. What is XM represents the molar fraction of your sample in the mobile phase, and XS represents the molar fraction of your sample in the stationary phase. So what, as a chromatographer, when you're optimizing the method, you have to optimize your method in such a way the equilibrium is always shifted from the right hand side to the left hand side. That means more and more amount of sample should come out of the stationary phase and it should come into the mobile phase so that it can flow out of the column, go to the detector and gets detected. That is your optimization process. That is your analytical, that is your method development process. Sometimes it can be time consuming also, especially when you are talking about a very, very difficult sample. But that is your skill. That is the whole concept of your method development. Evaluation of column, evaluation of chromatography columns. I just want to spend a minute on this because a very, very important slide for people who are working on GC or LC. Very common slide for GC and LC. The column is the heart of the system. You talk about GC, you talk about LC, column is the heart of the system. Unless your column is the right type, you will never get the required information. Your injection port may be injection technique may be very advanced. Your detector may be very sensitive. You have got a very powerful software. Everything is there, but your column selection is gone wrong. That means you are not going to get the desired separation. Ultimately, you are interested in the separation, and the separation will be given by the column. So we have to consider column as the heart of the system. And column is a consumable item. It is not a permanent item. At one point of time, you have to throw it out and go for a new one. Column is a consumable item. But then many times people ask, what is the life of the column? We face this question when we go to the industry. Somebody may ask, I am spending so much of amount, so much of rupees, so much of price. I am buying a column, and how many years I can use this column? Very, very difficult question to answer, because column life depends on so many factors. The type of sample is a major factor. How many samples you are analyzing per day is the type of factor, nature of sample, and ultimately how much care you take about the column. That's also a very, very important factor. So all these will ultimately decide what is the life of a column. Okay, there are cases where columns can be used for pretty long time. Like in perfumery industry, I've seen a customer using a column for more than 4 or 5 years, capillary column, because his samples are very clean samples. At the same time, I have seen another customer who are in the field of agrochemical industry, very corrosive samples. His column is getting eaten away with a period of 6 months or even less than a year. So he has to replace the column because the type of sample. One is a highly corrosive sample, another one is an absolutely clean sample. So it depends on that. Okay, now column, when you talk about column efficiency, There are different column manufacturers. They will approach you for their column and with their columns. And one person may say, my column is very efficient. I am giving you at this price. Another person will come and say, my column is much more efficient than the previous one, and I am giving you at a premium price. Now it is your duty to find out which one is more efficient. So column efficiency is always defined in terms of sharpness of the peak. When you are analyzing a sample, if the peaks are coming out in a very, very sharp manner, peaks are very narrow and sharp and symmetrical, the column is a highly efficient column. So column efficiency is related to or defined in terms of sharpness of the peak. Sharper the peaks, better is the efficiency of the column. And now this is to be defined in terms of certain parameters. There has to be certain variables with which we can actually show the efficiency. There are two parameters. One is known as N value, number of theoretical plates, and one is known as HETP, height equivalent to one theoretical plate. Number of theoretical plates is nothing but it's a totally imaginary concept. There is nothing like plate inside the column. It's a purely imaginary concept. Now, for a layman's language, I can tell you for the understanding of students, number of theoretical plates means, suppose if you consider a adsorption column, in HPLC we use a silica column. It's a very good adsorption column, normal phase column. So the material is a adsorbent material, silica. So when I am injecting my sample into the column, and the first available site, the silica contains a lot of surface selenol groups, SiOH groups, highly polar groups. They are called surface selenol groups. And the first available selenol group will adsorb the sample. So sample is getting adsorbed. But it cannot remain there permanently because your mobile phase is also coming and flowing. And after some time, the sample gets dissolved from the side, moves forward, another selenol group will take it. Again, it gets adsorbed. And after some time, again, it gets dissolved. This way, as the sample is moving through the column along with the mobile phase, multiple times the sample is getting adsorbed and dissolved. So, number of theoretical plate, in a very simple way, we can define it as the total number of times the sample is getting adsorbed and dissolved. Or you can say it's a total number of adsorption, desorption steps that are taking place inside the column. More number of times this is happening, better is the efficiency of the column. So that is what that total number of these steps, that is known as number of theoretical plates. It's an imaginary concept. So number of theoretical plate is high, your efficiency of the column is also high. So most of the time when you're buying a column, there will be a certificate of analysis, COA, and in which the manufacturer will be showing certain standard sample chromatogram, and you also will be giving certain values for N value. N values will be given, noted in the, to be given in the shown in the certificate. And if you want, you can replicate the same thing in your lab on a periodic at a periodic interval. So you as a user, what you can do when you are purchasing a new column, and the column efficiency is going to go down over a period of time because you are continuously using the column. And a general thumb rule is, when the number of theoretical plates becomes 40% of the original value, you can think of replacing the column. That means for a certain standard compound, number of theoretical plates was 10,000. Theoretical plate has no unit. It's only a figure, 10,000. That was when the column was brand new. Now you are going to use the column. Maybe after 6 months, 1 year, 2 years, you measure the number of theoretical plates, which is very, very easy now. You can get the value from the software. Now after a couple of years, whatever it is, you see now it has come to 4,000. That means from 10,000, it has come down to 4,000. Means it's come down to 40% of the original value. And that is the time you can think of replacing the column. You may be able to use the column still further, but the peak shape will not be very good. Peaks will become broader. The peaks become broader, resolution will be affected, reproducibility will be affected, all those problems will be there. Okay, so that is why column efficiency is very important. And some of these parameters form the system suitability parameters when you are trying to validate a method, especially in pharmaceutical industry. Method validation is very critical in pharmaceutical industry. And when you hold, there are a lot of parameters to be validated. There is a subset of that, what is known as system suitability. where all these things will come. Your column efficiency, your symmetrical, your tailing factor, all those things will come. So I'm not going into those details because our time will not permit. Let us finally, what is more important is getting a very good resolution. Everyone knows resolution is what is ultimately required by everyone. Every analytical chemist will require a very good degree of resolution for the sample. If you are losing resolution, you stand to lose information. The resolution should be very good. And there is a universal equation, that is what is shown on the slide. R is equal to, don't much bother about this mathematical equation. We can actually calculate the resolution. And the resolution what you're going to get in chromatography is influenced by three different factors. One is your column efficiency, that is your N value. Then second one is known as the capacity factor, that is small k dash value. And then there is another value which is known as selectivity value, that is A value. All the three factors will appear in this equation, and that ultimately will provide you the resolution which is represented by R. Now, as a practical thing, I can show you this. You look at this slide, the extreme left-hand side, R is equal to 0. In my sample, there are two different compounds, but they are almost coming together without any resolution. R is equal to 0. So what I try to modify my parameters and slightly improve my resolution. You can see the second this thing, you can R is equal to 0.5, but nobody will accept it. R is equal to 0.5 is totally unacceptable. Further modify the conditions, you get R is equal to 1. No, it's only 90% resolution, not a baseline resolution, nobody is going to accept. But come to the last one, R is equal to 1.5. It is a 100% baseline resolution, and that is accepted. So when we go to our customers, we normally advise them to optimize the conditions in such a way that you get a R value of at least 1.5. If it is more than 1.5, good, but at least 1.5 you should get. That is called a baseline separation. And you can also improve the resolution by different techniques. By changing the mobile phase composition in the case of HPLC, we can improve the resolution. Changing the column temperature and ramping rate in the case of gas chromatography. Changing the composition of stationary phase itself, and sometimes in the case of GC, changing the column dimensions, like length of the column, internal diameter of the tubing. That also will create lot of that also have got lot of influence on the resolution what you are going to get. Ultimately, when we come to GC side, gas is going to be used as a mobile phase. It has to be an inert gas. You cannot use a reactive gas. It has to be pure. It has to be inexpensive. And what are the common gases that can be used in the case of GC? We can use nitrogen, hydrogen, or helium. Okay. Mostly people don't use hydrogen because hydrogen, even though hydrogen is supposed to be the best gas, hydrogen is explosive in nature, so people don't prefer. Helium is not preferred because it is extremely costly. Unless we are going to discuss now GCMS where helium is required. But in the case of GC, we have got an option, we can go for pure nitrogen. So when you go to industry, you can see 99% of people are using pure nitrogen as the carrier gas because it is cheaper. And at the same time, you can get a very high grade also. Purity wise also, we can get 99.99 plus pure nitrogen we can get. We can see the purity what is required. The minimum purity that is required is 99.99%. What we normally call as 49 gases, 99.99 gases. So that's the minimum purity we want, because otherwise, if you try to use a commercial grade gas, the commercial grade gas will contain a lot of impurities those impurities may get introduced to the sample itself. Over and above that, it can even contaminate your system, contaminate your detector, contaminate your injection port, lot of problems can come. Even contaminate your column also. And so we have to use a high purity gas, and the recommended flow rate will depend upon what type of column we are going to use. We are going to briefly discuss that. We have two different types of columns in GC or GC. One is called a pack column, which is available locally, and another one is called a capillary column, which is always important. We are using a pack column. You can use a flow rate anywhere between 30 ml per minute to 60 ml per minute. Because the tubing is wider, ID internal diameter is wider, more amount of stationary phase can be there inside, and you can use a higher flow rate, 30 ml to 60 ml per minute flow rate is required if you are using a local column. But capillary columns are all imported. There is, as on today, there is no local manufacturer for a capillary column in India. All columns are, capillary columns are imported. And the ID is very small, it's a very thin tubing, and we can think of maximum 0.5 ml per minute to 15 ml, 15 ml per minute. That's a maximum flow rate allowed through a capillary column. And there also capillary column also we are going to segregate into different forms, in different types, depending upon their ID. Okay. So that is we are going to see. Now column material, columns can be made of stainless steel column. I mean, I am talking about local columns. They are known as pack columns. Stainless steel column, metal column, stainless steel columns are available. Even today, there are people who are using that. It is very cheap also. And or it can be made of glass. Glass is supposed to be the best material for making column. But the only problem is fragility. Fragility means it can easily break. That is, handling is a problem. Otherwise, it is a wonderful material. Then the next option is fused silica. Fused silica is a purified form of silicon dioxide. And today, whatever capillary columns you are getting in the market, they are all made of fused silica material. Fused silica is as inert as glass. At the same time, it has got more flexibility. It will not break like glass. So that's a plus point. You can slightly coil the column, and handling is quite easy. So that is why fused silica columns are preferred. Capillary columns are all made of fused silica. And packing material, you know, GSC and GLC, one is a solid material, one is a liquid material. And pack columns, you can get a pack column up to maximum 5 meter. Nobody will provide a pack column which is more than 5 meter. Most of the time people use either 1 meter or 2 meter. That is very common. And internal diameter can be 2 millimeter to 4 millimeter. Look at the capillary column, imported columns, their length is starting from 10 meter. And today we have columns which are more than 100 meters in length. Imagine a column which is more than 100 meters in length. And the ID starts from 0.1 millimeter and maximum 0.53 millimeter, 0.53 millimeter. So you can imagine the very, very thin columns, thin tubings that are used for making a capillary column. And this is a slide will show you very briefly. I'll tell you, based on the internal diameter of the tubing, capillary columns are divided into 3 types. One is a microbore column, where the internal diameter is just 0.1 mm. And there is another type called narrow-bore columns, and where it can be, the internal diameter can be either 0.25 mm or 0.32 mm. And the last category is known as a wide-bore column, where the internal diameter is 0.53 mm. So we have 3 different types of capillary columns: microbore column, narrow-bore column, and wide-bore column. For most of the normal applications in pharmaceutical industry or polymer industry or food chemistry, perfumery industry, flavor, we normally utilize a narrow-bore column, either 0.25 mm or 0.32 mm ID. 0.53 mm column has got certain advantages, but not for all samples. And 0.1 mm column, microbore column, is used when we want to do fast GC or fast GCMS analysis. I am coming to that later. Okay. Now let's quickly look at very fast. We'll go. I mean, where the main types of. I think this is coming and blocking my slide always. Okay, main types of capillary columns. There are 2 types of capillary columns. One is known as a plot column, and one is known as a WCOT column. Plot column stands for porous layer open tubular column. That's called plot column. And mind you, this column is used mostly for gas analysis, not for normal analysis. For pharmaceutical analysis or a normal chemical analysis or a food chemistry, nobody will use a plot column. But if I want to separate some very complex hydrocarbon sample in a petroleum industry, I will prefer a plot column there. So specifically for gas analysis, plot columns, porous layer open tubular column. And the second one is wall-coated open tubular column. That's the one we are normally using for most of the common applications. So WCOT columns are more versatile. It has got more utility. Different types of applications can be carried out using a WCOT column. whereas plot columns are extremely useful for gas analysis. Now you critically look at this wall-coated open WCOT column. You see a blue ring, and inside you see a yellow ring. And that blue ring represents your fused silica tubing. That's a fused silica tubing. Okay. And originally, when you actually look at the column, it's not blue in color. This is only for the representation. We have made it like that. So the blue part is actually representing the tubing that is made of fused silica tubing. And what is that yellow layer, what you see, that is a very, very thin layer of your stationary phase coated inside. It is only a very thin coating of your stationary phase inside the tubing. And this coating thickness can be in terms of microns. Today we have columns which have got coating thickness of 0.1 micron, and you can even go up to 5 micron. So depending upon the type of samples and applications, we can select the right type of column for our analysis. So the stationary phase is coated as a thin layer on the inside wall. That is the reason why it is known as wall-coated open tubular column. Otherwise, there is nothing. It's an open tube. That's why it's known as open tubular. You look from one side, the other side, you can see the light. I mean, open tube. It's an open tube. There is nothing in between. This the stationary phase is actually coated as a very, very thin layer on the inside wall of the tubing. That is why it is known as wall-coated open tubular column. Then what about porous layer open tubular column? Porous layer open tubular column, you see the red tubing is nothing but your silica tubing. And inside you can see, you see a lot of small circles sticking to the side. It is a stationary phase, but it is a porous material. It is an adsorbent material. It is not a liquid. It's a solid material. It can be a copolymeric material. It can be materials like, there are a lot of other materials, solid adsorbents like silica, graphitized carbon, lot of things are there. And they are all solid particles. And these solid particles are coated inside as a thin layer inside the tubing. So that is why it is known as porous layer. And all these particles are porous in nature. They are adsorbents. Basically, they are adsorbents. So that is why it is known as porous layer open tubular column. And there is one more type which I am not discussing. That is known as SCOT column, support coated open tubular column. But that's very rare use. I am not showing that. Okay. Now, what are stationary phases? Man, these are all applicable to GCMS also. Stationary phases. Most stationary phases are polymers. Most common for WCOT capillary columns, because plot columns, we know they are all adsorbent solids. Okay. And these stationary phases can be divided into two types. Either there can be polysiloxanes in nature. They are basically silicones, silicon polymers, polysiloxanes, or it can be polyethylene glycol, PG. Okay, so some of these can be non-polar, some of these can be, especially when you talk about PG, polyethylene glycol, they are highly polar, and we have columns in between also. So naturally in GC, columns can be divided into three types: non-polar columns, medium polar columns, and highly polar columns, depending upon the stationary phase. Okay, it's a long discussion. We can have a total discussion on the columns only, column technology and the type of column. That's again is a very major chapter. Stationary phase, one simple example, polysiloxanes. We can see the backbone is always a silica-oxygen-silica bonding, Si-O-Si bonding. That's a backbone, it's a silica backbone. Any polysiloxane column, the silica backbone, the silicon-oxygen bondage, that's a backbone. And on this backbone, we can put different groups. R can be different. R can be only 100% methyl. Then it becomes a 100% methyl silicon. R can be CS2, 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 and it is cyanopropyl. It becomes cyanopropyl siloxane. It becomes polar. Only 100% methyl, it becomes non-polar. I can buy CS2, CS2, CF3, trifluoropropyl, still more polar. Or I can put a benzene ring also. R can be a benzene ring. It will be phenyl polysiloxane. And depending upon how much amount of benzene incorporation is there, the polarity also can be varied. Okay, so there are different groups that can be added to the backbone, silica backbone. Thereby, you can create different types of stationary phases having different degree of polarity. For example, one of the very commonly used column in your GC and GCMS is a 5% diphenyl and 95% dimethyl polysiloxane. That's the structure that is shown there. Is a very popular column. Different manufacturers will give their own different trade names. DB5, RTS5, SPB5. I mean, that 5 stands for 5% diphenyl modification is there on the silicon backbone. So 95% dimethyl polysiloxane and 5% diphenyl modification. So it is a very, very popular column for different types of GCMS and GC applications. Then sometimes you will also come across a column which has got an MS, stationary phase MS or low bleed column. People will say DB5MS, RTX5MS. That MS stands for, it's a low bleed column. Bleeding will be very, very less. That means it's a very stable column. These types of columns are preferred for your GCMS analysis, because in the case of GCMS, we don't want the bleeding to take place. So we want a more stable column. So we prefer MS types of columns for GCMS analysis. So slightly the backbone is slightly modified. If you look critically at the structure, there is a phenyl or a phenyl type group is incorporated into the backbone itself. It is not a side chain. It's an incorporation inside the backbone. That is the, here it is a phenyl group is inserted into the in between the silicon, ocean, silicon, silicon, ocean, silicon bonding. So there is a bridge inside the backbone. And that is how it becomes more stable, less bleeding, better temperature stability, and this amount of phenyl groups also can be adjusted. And these type of columns will have an abbreviation like DB5MS, RTS5MS, SPB5MS, like that. That MS stands for, it's a low bleed column, which is preferred for a GCMS analysis. Polyethylene glycol columns are highly polar columns, and these are basically called wax columns, or FFAP type of phases are also available, DB wax, DB FFAP. FFAP stands for free fatty acid phase. It is nothing but polyethylene glycol where the free hydroxyl groups are esterified with 4-nitroterephthalic acid. And that becomes an FFAP column, free fatty acid phase, which is extremely powerful and useful for different types of polar compounds. But at the same time, please keep in mind, polar columns are less stable. You cannot go to a very high temperature, so you have to be extremely cautious while using a polar column. These are some of the common stationary phases which is used in industry and academia. DB1, DB5, DB35, DB624, DB wax. They are all from one manufacturer called JNW Scientific, which is a part of Agilent today. And then SG is an Australian company. They call their trade name is BP. They call it as BP1, BP5, BP35, BP20, like that. And then Rustec is another US company which we represent, and extremely popular company for GC columns. They are world leaders in GC capillary column manufacturing. And their trade name is RTS. They call it as RTS1, RTS5, RTS624. So every company has got their own trade names. Sample introduction, in the case of GC, we can analyze gas, liquid, and solid. But in the case of LC, we cannot use gas samples, only solids or liquids can be analyzed. And in the case of GC, we have two different types of injectors. If you are using a local column, which is a pack column, your injector is different. It is called a pack column injector. And if you are using a capillary column, your injector is different. It's called a capillary column injector. So at the time of purchasing the equipment itself, you have to decide what type of a column you are going to use. Accordingly, we have to configure the instrument with the right type of injection system. Otherwise, you'll have problems. So I am just skipping this. Coming to column oven. Column is always inside an oven. There are two different types of operations in GC. One is called an isothermal analysis, and one is called temperature programming method. Isothermal means you are completing the analysis at a constant temperature of the column. I am keeping the temperature of my column constant during the entire analysis. That's called isothermal. There is a equivalent operation in HPLC. We call it as isocratic. Similarly, in the case of GC, we also can change the temperature. We can program the temperature. We can start from a low temperature of the column, and gradually we can increase, and then we can go to a high temperature of the column. This is called a programming method. In the case of HPLC, the equivalent is gradient system. So there are equivalents in GC as well as LC. Today, when your sample is a very complex sample, we prefer a temperature programming method because that can separate and can give a wonderful resolution for various components present in your sample. And we are coming to the last part, detector. Detector is to indicate whatever is coming out of the column. So what is your process when you inject the sample into your GC, into the injector port, which is kept at a high temperature? Your carrier gas, nitrogen, is also coming to the injection port, and your sample vapor and nitrogen will mix together, will go to the column, travel to the column, get separated, will come out of the column, goes to a detector. And the detector is also kept at a high temperature. There is a thumb rule. Your detector temperature should be always more than the final column temperature by at least 15 to 20 degrees centigrade. That's a minimum requirement. Otherwise, if your detector temperature is less than the column temperature, condensation will take place. Detector response will come down. That sensitivity will be compromised, and it will get contaminated. Then you have to depend upon the service person to clean it. So you have to keep the detector temperature at least 15 to 20 degrees more than the final column temperature. And the type of detectors, we have different types of detectors available in GC. Some of the more commonly used detector, one is flame ionization detector. Second one is thermal conductivity detector, flame thermionic detector. It is also known as nitrogen phosphorus detector, flame photometric detector, electron capture detector, and finally our next topic, that is your mass spectrometer, is known as MSD, mass spectrometric detector, MSD. Out of these six, your TCD, FID, and MSD can be used for any type of samples. So that is why they are clubbed as general purpose detectors. Whereas items under serial number 3, 4, and 5, FTD, FPD, and ECD can be used for only selected type of samples, and they are collectively called selective detectors, or some people call it as trace level detectors, because they are used only for trace analysis, not for normal samples, not for normal concentrations, only for trace concentrations. Okay, so what we'll see, what is FID can be used for any type of sample which contains carbon and hydrogen, and the sample and any sample which can undergo oxidation in a hydrogen air flame. Flame ionization detector, you understand there's a small flame in the detector. We are going to ignite hydrogen and air in the ratio 1:10. 1 part of hydrogen, 10 parts of air. And normally we use 30 ml of hydrogen, 300 ml of air, and we ignite it. And a small flame is produced, which has got a temperature of approximately 2000 degrees centigrade. And when the sample is coming out of the column, it comes into the flame, it gets oxidized, and it is a thermal degradation. The sample is going to be, it's a destructive detector. I mean, it is thermal ionization is taking place because of temperature. Thermal ionization is taking place. Now, ECD is a wonderful detector. It's a wonder detector in GC. Depending upon, we could look at the amazing sensitivity. ECD, electron capture detector, but it is a selective detector, not for all compounds. It is used for extremely trace amounts of electrophilic compounds. Electrophilic compounds means any compound which has got affinity for electrons, which can attract electrons. For example, halogen containing compounds. And they are in very, very trace level, we can use ECD. FTD, flame thermionic detector, which is also known as nitrogen phosphorus detector. They are very selective to trace analysis of organic nitrogen or organic phosphorus containing compounds. Third one, FPD, flame photometric detector, is again a selective detector for phosphorus or sulfur or tin containing compounds. And TCD, thermal conductivity detector, everyone knows when even a basic, maybe at the very early stage in a college, you must have studied Wheatstone bridge circuit in physics. Wheatstone bridge circuit. The TCD is based on your Wheatstone bridge circuit, and it was considered as a universal detector once upon a time. But the only problem is the sensitivity is very low. If the concentration is less than 100 ppm or may at the most 50 ppm, less than 50 ppm, detection becomes very difficult. But when you go to any petroleum companies, when you go to any fertilizer companies, They are doing a lot of gas analysis where they talk in terms of concentration, terms of percentage level. 1% is how much? 1% concentration is 10,000 ppm. It's a huge concentration. TCD can be used without any problem. So TCD is widely used in those type of industries. If you go to Reliance Industries, if you go to RCF, if you go to GSFC, those type of companies, I mean petroleum companies or fertilizer companies, I mean you will find multiple number of GCs in their labs. With the most GC will have a TCD detector. Okay, so I'm just skipping these things. FID, most organic compounds can be detected. The compound has to contain carbon and hydrogen. It undergoes an oxidation, CHO plus an electron is given. There is a capture electrode above the flame that will capture the electrons and convert it into current. And very, very decent detector, very decent amount of sensitivity can be used for most organic compounds. ECD is a very, very selective detector. You have to be extremely cautious. You have to be extremely careful because the detector contains a radioactive isotope nickel 63. And if you want to install an ECD on your GC, you have to take prior permission from BARC. That is required. Without permission from BRC, you cannot import ECD and install on your GC because it contains a radioactive material. Extremely powerful for very, very, very trace amounts of electrophilic compounds. And you have to use ultra pure nitrogen as the carrier gas. Take extreme precautions while using the utensils, your glasswares, your pipettes or syringes, whatever it is, even the chemicals, you have to have a separate set for all those. And no contamination should take place. If contamination of the detector takes place, your life is going to be hell. Because even by law, we cannot, even the service person cannot open an ECD, whereas he can open all other things. This ECD cannot be opened because it can, because of radioactive material inside. Extremely powerful detector, extremely powerful detector. You can go to femtograms levels of detection, 10 to the power of minus 15 grams, femtograms levels of detection. FPD is again for phosphorus and sulfur containing compounds. I'm not going into the hardware details. Similarly, FTD is for nitrogen and phosphorus containing compounds. And the TCD is, as I told you, once upon a time, it was considered as a universal detector. But today it is not. Today, a true universal detector, the mass spectrometer, that is what we are going to discuss now. And qualitative analysis, and you can use, there are different methods for qualitative analysis, direct comparison of retention time, retention index, and all those. And EC can be used, and GC or GCMS can be used as a quantitative technique also. We have three different methods of quantification. One is known as normalization method. Second one is known as corrected area normalization method, where we take into consideration the response factor. And the third one is called absolute calibration curve method, under which there are two different types. One is called internal standard method and one is called external standard method. All these quantitative analysis methods are applicable for GC and LC. There is no difference at all. Okay. Now we are directly coming to your mass spectrometer. So I just gave you a background information about GC because many of the separation principles, the type of columns, everything is going to be same in the case of GCMS. What is differing there is only the type of detector. Instead of other conventional detectors, we are only talking about mass spectrometer. That's a mass spectrometric detection technique. And advantage of mass detector, MS detector has got a very distinct advantage over all the conventional detectors. We have seen a couple of detectors like FID, ECD, FTD, FPD, all those. There are a lot of others also like BID, SCD, a lot of others also. I have not touched upon that. They are all very powerful. No doubt they are all very powerful. So, but MS has got a edge over that. They have got a distinct advantage over all those detectors. While all the conventional detectors provide good sensitivity. Now you talk about ECD. ECD sensitivity is just fantastic. There is no question about that. I mean, very, very sensitive detector. But the problem is all those detectors will give very good sensitivity for the separated components. Column has to separate. The separation is the responsibility of the column. And the responsibility of the detector is only detection. Okay, so as the column is separating the compounds and sending it to detector, they are detecting with a high degree of sensitivity. But those detectors will not tell you what are those compounds. And if you want to identify those compounds, you should have reference standards. If reference standards are not available, you just cannot identify the compounds. You can only get a clean separation. No identification, no quantification. Okay. Whereas when you consider mass spectrometer, an MS detector can give a very high sensitive analysis. That means sensitivity is not compromised. At the same time, it can give a positive identification of the separated compounds without the requirement of an authentic standard. That's a plus point. That means you don't require a standard to identify the compound. In the normal GC, normal LC, you require a standard for identification. Whereas the case of GCMS, for identification, you don't require a standard. That's the biggest advantage. A lot of advantage in when you talk about perfumery analysis, when you talk about flavoring compounds, very, very complex hydrocarbons, and it's very difficult for us to get reference standards to identify them. So if you are having an MS detector can automatically identify what are those compounds separated by the column. That's a major advantage. That is the edge of MS over all those conventional detectors. Okay. Now let us see what is the simple definition of mass spectrometry. The basis of MS, that is mass spectrometry, is the production of ions that are subsequently separated or filtered according to their mass to charge ratio, M/Z ratios, and they are detected. The resulting mass spectrum is a plot of the relative abundance of the produced ions as a function of the M/Z ratio. Okay, so I will just explain this. The basis of mass spectrometry is the production of ion. That means it simply means the sample has to undergo ionization. So that is the basic requirement. Okay, I'll take a sip of water, just a few seconds. So that means the basis of mass spectrometric analysis is the sample has to undergo ionization. And we are going when we go forward, we'll see how the sample is going to be ionized. So the basic requirement is the sample has to undergo ionization, and it will produce different ions. And these different ions will be having different mass to charge ratio. Or in simple terms, you can say they will be having different mass numbers. And depending upon the difference in mass numbers, they are all going to be separated. They are going to be filtered. And then they are all going to be sent to the detector. Okay. And what is the output we are going to get from a mass spectrometer? It is a mass spectrum. So mass spectrum is going to be the output from a mass spectrometer. And the mass spectrum is nothing but a two-dimensional graph. It's an XY graph. On the y-axis, we have the mass number axis, AMU, atomic mass unit. The mass number is plotted on the x-axis. And y-axis is called the relative abundance value, or it is known as the relative intensity value. What does it mean? Relative intensity means when the sample is going to be ionized, it will produce, I can give an example. You take a glass bottle, and the glass bottle you drop it on the floor. What will happen? The glass bottle is going to be shattered. It is going to break down into pieces. Some may be smaller piece, some may be bigger piece, some may be medium piece. The weight of each piece also can be different. Similarly, when a molecule is going to be ionized, it is going to produce different pieces. And these pieces, what we normally call as the ions. And each one has got its own weight, its own mass. So the mass numbers can be different. So some of these pieces can be produced in larger proportion, and some other pieces will be produced in lesser amount of proportion. So that means their intensities can be different, and the relative intensities can be different. So what we are doing is we are plotting the relative intensity on the y-axis and the atomic mass unit or the mass number on the x-axis, and that is the mass spectrum. And that mass spectrum is going to be the deciding factor. And based on that mass spectrum, you are going to identify the compound. So in the case of mass spectrometry, in the case of GCMS, identification of the compound is based on the mass spectrum which the sample is going to produce. In the case of GC, normal GC, the sample identification is based on retention time. Retention time. But retention time has nothing to do with identification in the case of GCMS. We are only going to use the mass spectrum that is produced by the sample, and that becomes the identification technique for our sample. Okay. So basic requirement for an MS is MS detection. The compound has to undergo ionization. Ionization of the compound can be by different techniques that we are going to see. And before that, what is the objective of carrying out a GCMS analysis? Number one, that is our priority number one, separation and identification of compounds. That is qualitative analysis. If you are having a multi-component system, your sample contains different compounds. The first priority is to separate all these compounds with the help of a proper column. Okay, so that is your first priority, separation. That's a qualitative analysis. Okay, and then using your mass spectral library, you are going to identify what are those compounds. So you got a proper separation, and you also identified all the separated compounds with the help of mass spectra. Second priority is quantification. Having received a proper separation and identification, you are going to find out what is the content of each compound, what is the percentage of each compound, what is the concentration of each compound. That becomes a quantitative analysis. And the third priority is a high sensitive residue analysis. Nowadays, we talk about residue analysis. That means extremely low concentration samples, detection and determination, qualitative as well as quantitative analysis of very, very low residue samples. Talk about food safety. Today, we are talking about a lot of pesticide residues in food products. See, whatever milk we drink, drinking water, bottled water, vegetables, fruits, meat, fish, dairy products, everything contains pesticide residues, and it's a global issue that is being debated. And these many times these pesticide residues are present in extremely low concentration, maybe ppb level or sub ppb level. So their identification and quantification is a very, very critical thing. So a system should be capable enough to do that. And there are a lot of applications. This pesticide analysis is just one thing. There are a lot of bioanalytical applications, a lot of pharmaceutical applications, a lot of forensic applications, where your system will be looking for very, very high sensitive residue analysis. So these are the objectives of carrying out a GCMS analysis. And there is something called 4S values. There are 4 S. Number 1 S stands for sensitivity. Simple definition of sensitivity is change in the detector response when there is a change in the concentration of your target compound. That is all what is meant by sensitivity. People will talk about the sensitivity. I must say my instrument is very sensitive. My analysis is very sensitive. My detector is very sensitive. What is meant by sensitivity? This is the simple definition. Change in the detector response whenever there is going to be a change in the concentration of your target compound. That is your analyte. People talk about selectivity. Simple definition, relative freedom from interference. Especially when you talk about high matrix samples, especially food products, biological samples, forensic samples, all these samples contain unwanted things, unwanted interfering compound. These are basically called matrices. So the target determination in this type of compounds is very, very tricky, because many times all these matrices can interfere in the determination. So many times we can get a false result. We can get a false positive result. So that's very, very critical, especially when you are looking at some critical analysis, very, very trace analysis. So interference should not be there. So selectivity means freedom from interference. So when I say when my method is selective, I can, with confidence, I can say when I'm estimating something using this technique, no interference is going to take place. 100% freedom from interference. That is called selectivity. Speed of analysis is very important in today's corporate world. Speed of analysis means, suppose what is the output? Suppose one sample is getting analyzed in say 1 hour time. So when a very complex sample, it is taking almost 1 hour to complete. That means in a day, how many samples you can analyze? Maybe 5 samples, 6 samples, or at the most 7 samples, not more than that, because each sample is going to take 1 hour. Now, if there is a method by which this analysis time can be reduced, the 1 hour analysis time can be reduced to 15 minutes time or 10 minutes time. That means in 1 hour time, I can analyze minimum 4 samples. That means at the end of the day, my output is going to be more by 4-fold increase in the output. And that is what is the requirement of corporate world today. Give more and more output. In a given period of time, try to increase your output. Speed of analysis becomes very, very critical in that context. Solution, not just instrumentation. Whenever you are purchasing a very high-tech equipment like a GCMS or LCMS or GCMS, LCMS, you should get a complete solution for your requirement because it is a capital investment. So it has to provide you a total solution for your analytical requirement. This is a flow chart of a GCMS. SQ when I am writing is called single quadrupole because we also have got a much more advanced equipment which is a GCMS, which is known as TQ. That is called a triple quadrupole system. When we talk about only GCMS, it is a single quadrupole system. That's why it is known as SQ and the other one is known as TQ. Okay. So you have a sample. It contains multiple compounds. The sample, you can see the arrow. The sample is introduced into GC. GC contains a column. And column will separate these compounds. And one by one, it will come out. And it is come to the ion source. This is the first part of your mass spectrometer, ion source. And here the sample will undergo ionization. The sample will be converted to ions, fragments having various mass numbers. And then all these fragments will be separated by the mass filter, or it is also sometimes known as mass analyzer. And the responsibility of this mass filter is to separate all these fragments based on their mass number. And they're all sent to the detector, which is nothing but an EMT, electron multiplier tube. And that is going to give a signal. And the signal can be processed by your process. You get the output, that is your mass spectrum. Now look at this ion source, mass filter, and detector. All three are connected to a very powerful vacuum system. Your GC is open to atmospheric air and your MS is kept under a deep degree of vacuum. So that is why it's a hyphenated system in which one part is open to atmospheric air and the second part is put under vacuum. And you can see also one more arrow, sample direct inlet. That we'll discuss after a few slides. I am going to show especially that is useful for pharmaceutical people. Others may not require it, but pharmaceutical people, this is a very, this direct inlet technique is a very useful accessory for pharmaceutical analysis that we will separately discuss. The normal course is sample is to be injected into GC. GC column will separate. Compounds will come one by one from the column, come to the ion source, undergo ionization, converted to fragments or ions, having various mass numbers. They will all be separated by your mass filter. They all will be taken to the EMT, that is electron multiplier tube. It will give an output which is nothing. It is nothing but the mass spectrum. Okay. Now different ionization modes are there. By default, if you take any GCMS, your ionization mode is electron impact ionization. Electron impact ionization is the default mode of ionization. That is the one which is normally used for any type of qualitative analysis. If you are interested in finding out the qualitative analysis, then you have to undergo electron impact ionization. You have to use electron impact ionization. You get a lot of information about the structure. Then there is an optional method called chemical ionization. That is soft ionization technology, low energy technology. You will get a lot of information about the molecular weight. Okay. So electron impact is like this. Your sample is coming from the column. It will come to the ion source. And there are two filaments here. And the filament is actually emitting electrons at 70 electron volt energy. And these filaments will, these electrons will come and hit the sample molecule. And it will be fragmented into different pieces. The molecule is going to be fragmented. And each fragment is having a certain mass number. And then they will be separated by mass filter and detected by your detector. And what you see at the bottom is the mass spectrum. This is the mass spectrum of methyl stearate, methyl ester stearic acid. Okay. Now, positive chemical ionization, basically for the determination of molecular weight of the compound, you require a reagent gas here. Your normal carrier gas is helium in the case of GCMS. But when you have a PCI, For positive chemical ionization, you have to have a reagent gas. What we normally do is we introduce a reagent gas into the system, and then this reagent gas will be bombarded by electrons. And see, for example, we can use methane. Methane is a very commonly used reagent gas. Methane is bombarded by electrons, and methane will get converted to two unstable ions, C2H5 plus and CH5 plus. They cannot remain in that state for a longer time. They will collide with your molecules, your actual sample molecules, and the extra proton is given to the sample molecule, and C2H4 and will go to the C2H4, which is a more stable form, and your sample will get an additional proton. It is nothing but a protonation reaction that is taking place. So your molecule will have an increase in the molecular weight by 1 unit. So that is why your molecular ion, the most prominent ion what you see in positive chemical ionization is an M+1 ion. That is molecular weight +1, because that +1 is because one hydrogen has come. It has received a proton from the C2H5 or CH5 plus unstable ions of your reagent gas. So it is a protonation reaction that is taking place. Your sample will acquire a proton, molecular weight will increase by 1 unit. And if you look at the methyl stearate PCA spectrum below, you see a very, very prominent fragment at 299, because methyl stearate molecular weight is 298. So 298 plus 1, it has become 299. So it is very easy for you to understand what is the molecular weight of your compound by looking at the PCA spectrum. This is a comparison between EA spectrum and PCA spectrum. EA spectrum is very, very complex, but it gives a lot of information about your structure, and PCI gives the right information about the molecular weight. So that you can consider it as complementary. Both can be considered as complementary techniques to each other. Then there is called negative chemical ionization. The negative chemical ionization is only for electrophilic compounds. The samples which have got affinity for electrons. Same thing, we can use methane also here, but here being in the case of negative chemical ionization, we are changing the polarity of the lenses through the software, and the negative ions, because the sample has got an affinity for electrons, it forms negative radicals, and they are collected and positive ions are discarded. So thereby very, very small amounts of electrophilic compounds can be very precisely determined and quantified and qualitatively identified using a negative NCA mode of ionization, called the NCA mode of ionization. So in all, we have 3 different modes of ionization. Electron impact ionization, which is the most widely used one, which gives a lot of information about the structure. Then we have PCI, that is positive chemical ionization, which gives the information about the molecular weight, and negative chemical ionization for the qualitative and quantitative analysis of trace amounts of electrophilic compounds. Mass analyzer is an integral part of the MS, which is responsible for the separation of ions produced in the ion source on the basis of mass number. We know whatever fragments are going to be produced in the ion source, they will be separated by the mass analyzer or the mass analyzer, or it is also known as mass filter, and that is the responsibility of mass analyzer. So your quadrupole is a mass analyzer. That is what we are going to see now. So there are different types of mass filters or mass analyzers. Magnetic sector is there, but not generally very frequently used, not commonly used in industry, because very, very high cost is very high, but it's very, very high resolution. Normally used only for high-end research activities. Quadrupole is the one which is most commonly used in industry, quadrupole, QP. Then we have got time of flight for high molecular weight compounds, biopolymers, high molecular proteins and peptides and all. Time of flight, high mass range compounds. Then there is another one known as ion trap. That is also a benchtop. Ion trap is a benchtop mass analyzer. Quadrupole is also a benchtop mass analyzer. But ion trap has got its own certain inherent problems also. That is why more and more people are using quadrupole. This is what is basically like a quadrupole mass spectrometer. Using the extreme left-hand side, you have ion source, but the sample has undergone ionization. When it has come from the column, the sample molecule was hit by electrons with 70 electron volt energy. The sample has undergone fragmentation. Lot of fragments are produced having different mass numbers. They're all separated by your quadrupole. So in between is the quadrupole, and the extreme right hand side is your detector, which is nothing but a EMT, electron multiplier tube. How these fragments are separated, that's what is this slide is going to show. Quadrupole means 4 different rods, cylindrical rods, and 2 are at the one at the bottom, 1 at the top, and 2 at the sideways. That's arrangement, quadrupoles. And what we are going to do is across one pair, we'll apply a DC voltage. Suppose this is this one and this one, we'll apply a DC voltage, and across the other 2, we'll apply radio frequency. So at any point of time, there is a ratio of DC to RF, and depending upon this ratio, only one fragment from the ion source will get attracted, and it can pass through the space between these 4 rods without touching it, and it will go to the detector. But our intention is to take out all the fragments. So what we do, we continuously change this ratio DC to RF voltage, so that for every single ratio, one particle will come out, one fragment will come out, and it will go to the detector. This happens in a very small period of time. You can say maybe microseconds, or it's very small period of time this happens. And all the fragments of the ion source will be taken to the detector, and the detector is going to give a output, which is the mass spectrum. Capabilities of a quadrupole system: it can carry out excellent qualitative analysis for a multi-component sample, can provide very reliable library search details. That is one of the most important characteristics of a quadrupole system. Your library search is going to be very authentic, has got very good quantification capability also, and very easy to use. So these are some of the capabilities. So this is how it looks like. I'm just skipping it. And how to improve sensitivity: quadrupole uses SIM mode of analysis. That is what we are going to see now, SIM mode of analysis to increase the signal, and ion trap systems use MSMS mode to reduce the noise. But both will result in a better signal to noise ratio. There are 2 modes of operations in GCMS. One is a scan mode and one is a SIM mode. Scan mode means we are continuously scanning from, say, one atomic mass number to another atomic mass number. Normally we scan from, say, 40 AMU to 400 AMU or 500 AMU, like that. Okay. And we look at, the detector is going to look at every fragment that is going to be produced. So scanning is performed continuously at a regular interval from a lower mass number to higher mass number. So your sample, depending upon the structure, may produce 15 fragments, 20 fragments, but then all the fragments will be seen by the detector. Gives a lot of important qualitative analysis, structural information you can get from the scan mode of analysis. Qualitative analysis, if you want to do, you have to work in the scan mode of operation. But if you want to do quantification, you have to work in the SIM mode of operation. SIM stands for selected ion monitoring. See, your sample is producing 15 fragments or 20 fragments, but all fragments are not very intense. Out of these 20 fragments, we are going to select only 3 or 4 or 5 prominent fragments. And these fragments we are going to feed in the system, in the software, and the detector will only look at those fragments. That is why it is known as selected ion monitoring. Who is going to select? The user has to select it. You have to select and tell the software, these are the fragments we want to monitor. The detector will only look at those fragments, and other fragments, it will be blank. And what is the advantage? You get a much more sensitivity for quantitative analysis. So please understand, if you want to do a quantitative analysis in GCMS, work in SIM mode. And if you want to only identify a compound, work in scan mode. This is a SIM mode. Say, for example, my sample had given me multiple components, multiple fragments, but I was interested only in 3 fragments, MPI 54, 72, and 152. So these 3 fragments were selected, and then the detector will only look at these 3 fragments, and I get a much better sensitivity for the analysis. So that's important. Vacuum is also very important in MS, because vacuum is applied to pump out the residual gases like air and water vapor, etc. When the instrument is not in the on condition, when you are shutting down the instrument, outside air will go inside. And the next day when you are coming and starting the instrument, what the vacuum pump is doing, it is actually taking out all the air, water vapor, everything, whatever is there inside the system, it is pumping it out, so that when your sample undergoes fragmentation, there will not be any collision between your sample fragments and these residual gases like nitrogen that is present in water vapor, that is present in atmospheric air, water vapor and all. So to take out those residual gases, we are applying vacuum, and the vacuum is very important, and the vacuum level also has to be very high if your quality of your mass spectrum is to be very high. So quality of your mass spectrum also to a certain extent depends upon what is the degree of vacuum you are achieving in a system. Okay, this is the hardware. I mean, so you can see this, there's a column here. This is the injection port. We are injecting the sample with the syringe. This is your injection port, heated injection port. This is the column, and one end of the column is connected to the injection port. Another end of the column is passing through an interface, heated interface, and it is coming inside your mass spectrometer. So this whole portion is your mass spectrometer. This is your ion source. This is your quadrupole system, and extreme backside is your detector, that is the EMT. And what you see here is the turbo pump. It's a turbomolecular pump, which is actually creating the final degree of vacuum inside. It's like an aircraft engine. An aircraft engine is also a turbomolecular pump, but much bigger size. Here it is a miniaturized size. That's only difference. Variable ionization voltage I'm skipping because these are all basically software operation. So I'm just skipping it. And how do we find retention time? Many times when you're using the column, over a period of time, the columns may be slightly getting aged. There is a common process known as cutting the column. From the injection side, some 10 centimeter, 15 centimeter column can be cut. When the column is cut, there can be an effect on the retention time. Retention time sometimes can change. So if a column was when brand new, when there is a 60-meter column, after some time, so we are getting some sample analysis, certain retention times. When after certain times the column was getting older, cutting the column length has come down. Now the retention time is going to change. For the same sample, the retention time is going to change. So how the system will understand the same compound, because the retention times are totally different now. So there is a process by which we can actually find out what is the actual retention time, which is basically known as a retention index. And this is a process basically for retention index and retention time. Retention time is condition dependent. If you are changing the condition, your retention time will change. And if your retention index of a chemical compound on a given stationary phase is always constant irrespective of the conditions. So that is the importance of your retention index. So once you know the retention index of a compound, you can actually find out what is the actual retention time. And to find out the retention index, there are certain standards available. They are normal paraffin saturated hydrocarbons like C20, C21, C22. And by convention, the retention index of a saturated paraffin is carbon number multiplied by 100. Correct. That means for C20 hydrocarbon, retention index Ri is 2000 because 20 multiplied by 100. C21 it is 2100, C22 is 2200. Okay. And suppose when my sample is injected, it is coming between C21 and C22. I can calculate the retention index of my sample. How do we do that? Suppose you take C21 and C22, the distance between the midpoints of C21 and C22, you can see these two lines. If this distance is divided into 100 equal parts, and now my sample is coming on the 42nd division. So it is coming between C21 and C22. C21 Ri is 2100, C22 Ri is 2200. So obviously, you know, your sample has to have an Ri between 2100 and 2200. And it is exactly coming on the 42nd division of this. So your Ri is 2100 plus 42 is 2142 is the retention index. This retention index of this particular sample is going to remain same under any conditions. Whatever conditions you, analytical conditions you change, this 2142 will remain same on the same column. It will change only if you change the stationary phase. So that's a better way of understanding the retention time of the compound, and better way of identifying the compound whenever there is a change in the column dimension, or you are changing the column. A new column is coming in place of an old column. There can be variations in the retention time. So how to identify? We make use of this in GCMS. Okay, I mean, these things I'm just skipping. Fast GCMS, today I told you what is the corporate requirement to increase the output, because you have to reduce the analysis time. So there is something called fast GCMS analysis. You can actually reduce the analysis time, but there are certain parameters required. Your oven should have a very, very high heating rate. The oven what we are providing, it has got a heating rate of 250 degrees centigrade per minute. And then you have a very high head pressure. Head pressure is the pressure with which you are actually injecting the sample into the injection system. Your GC is a high pressure system. Normal GC, we apply around 450 kPa for introducing the sample. Okay, but when you are talking about a microbore capillary column, which is required for fast GCMS analysis, this 4 kPa pressure is not required, is not sufficient. You have to use minimum 900 kPa pressure. Then only the sample will go into such a narrow tube which is under a very high pressure. And we can provide 970 kPa. So that also is actually satisfying one condition. You should have a very high splitting ratio, because extremely small quantity of sample only will go to these type of narrow columns, like 0.1 micron microbore columns. The amount of sample will be extremely small. So you should have a very high split ratio. Split ratio is a parameter by which you can actually control the amount of sample that is going into the column. And your mass spectrometer should have a very, very high scanning rate. And we can offer a scanning rate of 20,000 atomic mass unit per second. That's a scanning rate we are providing on our mass spectrometer on GCMS, 20,000 AMU per second. This is an example of a perfumery sample. Fast GCMS analysis, you see 2-1, and the upper one is an analysis under normal GCMS condition. It has taken approximately 50 minutes, roughly 1 hour. The same sample is analyzed on a microbore column under fast GCMS analysis condition, and the analysis was completed in less than 10 minutes time. So that means in 1/5 of the total time you are completing the analysis. That means in the normal time, whatever it has taken time, so 1 hour out, you may be able to analyze 4 or 5 samples. So that means your productivity is going to be more 4-fold or 5-fold. So that is the requirement, today's corporate requirement. So that is why we have introduced this model, fast mode of analysis in the case of GCMS. Now, many times when people may ask, when you are actually reducing the analysis time, what will happen to the resolution? Whether the sample compounds will get mixed up? Not, that is not possible. You can see one slide here, normal mode and fast mode. In the previous chromatography, in the slide, I put a bracket here. This, you can see this red colored bracket, and that portion is magnified here. And you will see the resolution is going to be absolutely same for normal mode as well as fast mode. We are not compromising on the resolution. Okay. This is one accessory. I was talking about direct inlet system. Only pharmaceutical people will be interested in this. For this, your sample has to be a very, very pure sample. It cannot be a mixture. It has to be a single sample. It has to be 100% pure sample. And in that case, instead of injecting into GC, you can directly push the sample into the MS with the help of a probe. And this is the probe what I've shown on the left-hand side. It's a very small one. You can put it inside the pocket also. The small probe, there is an opening here, and there are small, very tiny quartz cups are given. Quartz cups are given. And you can put a very tiny, just a very tiny grain of your sample. This is a solid sample. Or if it's a liquid sample, you can hardly take just 1 microliter, put in the quartz cup, and that cup will sit here. There's an opening here. That's a place where you keep the quartz cup. And this direct inlet, that is the probe, can be pushed into the mass spectrometer without affecting the vacuum. And you can complete the analysis within a very short period of time, like 5 to 6 minutes or 7 minutes. You can complete the analysis. This probe can be heated up to 500 degrees centigrade. We have different heating rates like 5 degree, 10 degree, 20 degree, 40 degree, 80 degrees centigrade per minute. And imagine heating temperature going up to 500 inside vacuum. So the effect will be much more. That is the reason why we are able to analyze some of the totally non-volatile samples also using a DI probe. Okay, otherwise non-volatile samples cannot be analyzed by GC. I told you that's a limitation. But if you are having a DI probe in a GCMS, We can even analyze a non-volatile samples because the temperature can go to very high temperature. Under the effect of vacuum, the effect will be much more. This is an anti-BP drug, DAMS analysis. We have introduced the sample directly into the MS, bypassing the GC column. And we got the mass spectrum. We can go for the library search. We can find out what is the molecular formula, molecular structure. And if I have the CA facility, even I can find out what is the molecular weight of the compound. And what is the time taken for that? Hardly 6 to 7 minutes time. So that's a major advantage. This is a polymeric material. I can use a direct inlet for that. And where I have taken the temperature or the probe up to maximum 500 degrees centigrade. And then I could get the mass spectrum of the polymeric material. These are some of the accessories. You can have an auto sampler. You can have a headspace analyzer. People who are working on water systems for volatile compounds and semi-volatile compounds in water. We have an attachment which is known as a PNT system, purge and trap system. People who are working on environmental samples, we have an accessory known as TD system, that is thermal desorption system. All these can be attached to our GCMS. And people who are working on polymeric systems, polymer composition, there is something called a pyrolyzer, the PY, pyrolyzer that can be connected to the GCMS and you can study the polymer composition. Otherwise, normally polymers cannot be directly analyzed because they are totally non-volatile samples. But if you have a polymer pyrolyzer attachment on GCMS, we can study any type of polymers. And we have got libraries also for that. Polymer libraries are also available. And some of the applications of GCMS, that's the last part of our discussion. GCMS has got wonderful applications in various fields such as pharmaceuticals, pesticides, perfumery industry, food analysis, petroleum, polymers, environmental samples, biomedical applications, forensic applications, spices and essential oils, perfumery oils, textile applications, rose applications, biofuels, and biotechnology. There's a long list of areas where we have got wonderful applications of GCMS. Topping the list is pharmaceuticals for residual solvents in API, because everyone knows API, there are residual solvents which have to be determined as per USP method number 467. USP method 467 is to be used for the determination of determination of residual solvents in API. Okay, now identification of intermediates in API, impurity profiling of finished API, analysis of raw materials, molecular weight of pure drugs, residual solvents in packaging material for pharmaceutical products. All these are very, very important applications which can be achieved with the help of a GCMS. This is a residual solvents in API. There are two different techniques. One is known as a syringe technique. That is what I'm showing here. The sample is taken in say 20 ml vial. I mean, headspace analysis is a totally different topic. It's a long discussion. I'm not going into those details because it will take a very long time. So this is what is happening. The sample is taken inside, heated, the vapors will come out, but the bottle is sealed, so it cannot go out. So there is an equilibrium process. Once the equilibrium is established, a syringe will automatically come, pierce the septum, take a certain amount of vapor, and it will go and automatically inject into the GC column. And this is what is known as a residual solvents in API in pharmaceutical industry by syringe technique. But today, this technique is not approved by USP. USP does not approve this technique. It was going on for quite a long time. But now what we are doing is a transfer line technique. Today, USP recommends a transfer line technique for residual solvents estimations in API. And we have got an equipment which is known as HS20, which utilizes a transfer line. So here there is no syringe mechanism. The vapor created in the bottle, you can see these bottles, the vapor created inside the bottle, the vapors are coming from your drug and they will be transferred to the column through a transfer line. This is known as a transfer line mechanism. And that is what is now being used in most of the pharmaceutical companies. So we have got a equipment for that, one of the most efficient headspace sampler HS20, which utilize the transfer line mechanism for residual solvents in API. And this is a typical GCMS analysis of residual solvents in API class 1 solvents. All those pharmacy students will be knowing the residual solvents in API. They are classified into 3 different classes, class 1, class 2, and class 3. Class 1 solvents are the most carcinogenic, more toxic solvents which should not be present. And their limits are also very, very stringent. There are 5 different solvents: 1,1-dichloroethene, 1,1,1-trichloroethane, carbon tetrachloride, benzene, and 1,2-dichloroethane. And they can be well separated with the help of a RXI 624 SIL MS column. 0.32 mm ID. It's a narrow bore column, 30 meter length, and the film thickness is 1.8 micron. And 624 column is a medium polar column. Is a 14% cyanopropyl modified 86% dimethyl polysiloxane column. It is a wonderful column for different types of samples, and that is one column recommended for the class 1 solvent separation by USP method. This is a CA spectra of a drug sample, and from this we can easily find out what is the molecular weight of this drug. See, now you see at the prominent fragment, which is an M+1 peak, is coming at 208. Your molecular weight of the drug is 207. So it's a CA mode of ionization used in GCMS for the determination of the molecular weight of a drug sample. These are some of the samples analyzed in pharmaceutical industry by DA, direct inlet mode. For example, on the left-hand side, you see a steroid, prednisolone. Normal case, I cannot directly inject prednisolone into my GC unless otherwise I'll have to convert it to TMS derivative, trimethyl-silyl etherification reaction I have to carry out. Convert it to TMS derivative, then I have to inject into my column. Takes time, derivatization is required, reagent is costly, lot of things. But if I have a DI, I can, without all this, I can directly introduce the sample into my MS. I can get all information within a short period of time. This is again another drug. You can see that is reserpine. So these are all directly introduced into the mass spectrometer with the help of a probe. That is why this direct inlet probe has become a very, very interesting tool or an accessory for pharmaceutical people. Okay, these are analysis of herbal drugs. Herbal drugs are highly polar samples. They cannot be directly introduced to the column. First of all, the column can be spoiled. Many of the compounds may not come out. Highly polar compounds, peak shapes will be very bad. Lot of problems unless you go for very, very highly complex derivatization methods. It's very difficult to analyze by GC. But if you have a DI, you can directly introduce this sample into MS, and you can get the mass spectrum. You can go for an identification. So it is not a GCMS analysis; it's a DIMS analysis. And nowadays we talk about genotoxic impurities in pharmaceutical products, and GCMS can be very conveniently used for the determination and the quantification of genotoxic impurities. One class is shown here, methane sulfonic acids, and they can get converted to methane sulfonic acid esters. Here you have shown some typical examples like methane sulfonic acid ester, benzene sulfonic acid ester, like basylates and methylates and all, and paratoluene sulfonic acids, tosylates. So all these are genotoxic impurities. Many of them are carcinogenic in nature, and they can be separated and quantified by and identified by GCMS. This is a typical genotoxic impurity analysis by using GCMS. You can see so many are getting separated, and we have libraries for this, and we can identify, and with the help of standards, we can also quantify them. Genotoxic, another type of genotoxic impurities, alkyl halides. Many of these alkyl halides are used for alkylation reactions, but many of these alkyl halides are also toxic in nature. Many of them may be carcinogenic in nature. So we used the GCMS, and there is a mode of operation which is known as FASST mode. I'm not going into those details. FAST is, but there is a fast, simultaneous SIM and scan mode of operation, because a qualitative analysis and a quantitative analysis can be carried out together. So these genotoxic impurities are analyzed by GCMS and for the qualitative and quantitative determination. And of late, many of the pharmacy people may be knowing, these are the nitrosamines determination in some of the certain groups of drugs. It has become, that is the one which is running now. It's a current topic by itself, determination of nitrosamines. There is a list of about 7 nitrosamines, and 2 typical examples are shown here, NDMA and NDA. N-nitroso dimethylamine, N-nitroso diethylamine, NDMA and NDA and NDMA. And these are to be very precisely quantified. And we can do this by a GCMS along with the headspace. There is also a USP standard official method using GCMS HS. And we can precisely quantify, determine, qualitatively determine and quantify. And these nitrosamines, which are present in very, very small concentrations, there are stringent limits for these compounds. This is one of the latest development in pharmaceutical industry. And we can go for quantification. So these are chromatographic overlay from 2.5 ppb to 10 ppb. We can create calibration curve and we can precisely quantify what is the NDMA content or NDA content in the pharmaceutical product. So that is what is nowadays we have generated a lot of data for most of the major pharmaceutical companies in India. Shimadzu has accumulated data by analyzing different types of samples. And GCMS in biomedicals, there is also a very upcoming area. GCMS is an important tool in neonatal screening for metabolic disorders. Especially when a child is born, NBS has not become official in India. NBS means newborn screening. But some other European countries and US and even Japan, NBS has become mandatory. The child is born, the child is to be screened for certain disorders. And then the treatment can be decided. Maybe some of the metabolic disorders, the treatment can be decided and the problem can be taken care of. Otherwise, the child may grow up with some permanent disability and other problems. For this, what is the starting material? The urine collected from the child. Urine samples for the patients are subjected to proper sample preparation because urine is a biological liquid. It's a highly matrix infested sample. Lot of sample preparations are involved, like SPE, solid phase extraction techniques are involved. And in the urine, from a human being, when the urine, there will be a lot of carboxylic acids getting excreted. And these carboxylic acids are getting formed inside our body because of different types of metabolisms. And in a healthy human being, there is a certain profile for the carboxylic acid. And if there is a disorder, the profile of the carboxylic acid can change. And we have a separate software which is known as IEM software, inborn errors of metabolism software. And using that IEM software, we can actually identify what is the disorder the child is having, and then the physician can decide what is the treatment to be given. So for this, a urine sample from the child is subjected to proper sample preparation and cleanup procedure and analyzed by GCMS for the presence of certain carboxylic acids. These carboxylic acids are to be extracted. They are to be cleaned up. They are to be purified, and they are to be converted into TMS derivative, trimethyl ether derivative. Then we inject into GCMS. Then we get a profile like this, a urine profile. And this urine was collected from a child after 3 days of birth. This data was created in Shimadzu, Japan lab. And then you go for a library search along with an IEM software. The disorder will be, they will show what is the disorder the child is having, if at all the child is having a disorder. Otherwise, there is no problem. And then these are the data that will be used by the physician to decide what is the course of treatment that is to be given, that is to be decided. And GCMS has got wonderful applications in food industry also, analyzing flavoring compounds. Lot of flavored foods are available in the market nowadays. And these are all synthetic chemicals that are added to give a certain flavor. And you can use a GCMS many times in combination with the headspace sampler also. You can identify what are the flavoring compounds in foods. Identification and estimation of residual pesticides in food. Another global issue today. Pesticides in almost all the food products. And we have to have, there is a long list of pesticides that are possibly, that could be possibly present in many of the food products. And they can be easily identified and quantified by GCMS. It's a major branch by itself. Determination of residual solvents in packaging material. That also can be done by GCMS in combination with the headspace sampler. Analysis of coffee aroma by GCMS SPME technique. SPME stands for solid phase micro extraction. It's a sample extraction technique. SPME probes are available, and different types of probes are available. So you can see the last one here. It is known as a conventional probe. SPME fiber, different. These are basically polymeric probes we are providing, and which has got adsorption characteristics. So when this probe is put inside a bottle and the bottle contains some sample, which contains some aroma material or a flavoring compound, this probe will actually absorb those materials. And then after some time, that probe is taken out and introduced to the GC injection port, and whatever is adsorbed on the surface will get dissolved and will go to GC column, and we can identify what are those compounds. That is basically called SPME technique, solid phase micro extraction technique. So there are nowadays some new types of probes have come. They are known as SPME arrow probe, SPME arrow. You can see this, the probes are little wider. The surface area is much higher. Here the surface area, the volume, phase volume, phase value, phase means the absorbing phase, the volume was only 0.6 microliters, a very thin probe. And nowadays, the latest development, very recently we have come out some new probes where the volume is increased. That means it has come to 3.8 microliter. Now we have probes which are having a volume, surface area volume of 10 microliter, and these are known as arrow probe. That means the absorption capacity of the probe is increased. That means your sensitivity of analysis also can be increased. In the next slide, you can see this is the coffee aroma sample. And the bottom portion, you can see it is by a normal probe. And the upper one is, we have used the arrow probe. And you can see more number of compounds are detected. Coffee aroma is a highly complex material. Sometimes you can have more than 100, more than 150 compounds can be separated in coffee aroma. It's a very, very complex sample, flavoring compounds. You can see the sensitivity is increased manyfold when we are using an arrow probe, SPME arrow probe, as against a SPME normal probe. And then we can see the sensitivity difference also. Here we have detailed some of the important compounds are shown here, like dimethylfuran, 2,3,5-trimethylfuran, limonene, phenyl acetate. And the yellow color is the sensitivity due to the arrow probe, and the brown one is because of the normal probe. So that means by using an arrow probe, today we can get a much better sensitivity in difficult food samples, different types of food samples, flavoring compounds, aroma products. I mean, this is a very, very important area today, SPME analysis using GCMS. And this analysis of pesticides and food products by GCMS, you can see almost about 53, 54 pesticides are separated by a higher resolution capillary column. And all these are identified with the help of a library. There's a long list of compounds. See, almost all the compounds are identified by SIM mode. And they have shown some of the SIM modes for quantification. We have done this normal qualitative analysis is done by scan mode, and quantification was done by SIM mode. And these are all pesticides that are quite possible in different types of food products. The list is much more. It's only a partial list I have shown. The list of pesticides that are possible, region to region, it can be different. The type of pesticides Japan, may be present in Japanese foods, may be different from the type of pesticides that can be present in Indian region. So region to region, there can be pesticides. Japan has come out with Japan regulatory body has come out with a long list of pesticides. I think about 900 numbers of pesticides that are possible in food products. Not necessary that all the 900 should be here. I mean, it can vary from region to region, but they have compiled a list of around 900 possible pesticides that can be present in different types of food products in different regions and different countries. And GCMS, and nowadays we are even using GCMS for that. GCMS also can be used, but today we have gone one step ahead and we are using GCMS for that. And I think this will be the last slide. That's a typical forensic application, blood alcohol by GCMS and GCFID, and we can actually go for a comparison. Blood alcohols analyzed by a normal GC, where we have used an FID detector, and what are the volatiles that are found in blood: methanol, ethanol, isopropanol, and acetone. And normal propanol was used as an internal standard for the quantification. The same sample we analyzed by GCMS, we are getting a very matching profile. Only the retention times are different because in the case of MS, there is a vacuum effect is there. So naturally, your retention times will be on the lower side. But there are certain flow methods which we can actually match the retention times in normal GC and GCMS. A constant linear velocity mode and all we can utilize. And today we have facilities for matching the retention times in a normal GC and a normal GCMS. So like that, when we go for a long discussion, there are plenty of applications available for GCMS and the various segments and pharmaceuticals, food chemistry, environmental samples, forensic samples, perfumery samples, spices, paints and polymers, and perfumery system, biotechnology, clinical applications. The list is a very long one and plenty of applications are available. And depending upon the type of industry where you are in, the type of segment where you're working in, you have your own, the applications will be different. And we have got different columns available catering to each and every application. And the only thing you have to optimize the method to suit your application. That is the responsibility of the person who is sitting and developing this method and optimizing this method and validating this method. So I think that's the last slide. And here are my contact details. I have given my email, both office and personal, and my mobile number in case if anybody wants to contact me in future for any of those and whatever possible help I can do, I'll be too happy to do that. And you're most welcome to contact me anytime, either on mobile or on my personal ID or official ID. You can, if you want, you can note down this. And that's the last slide. And I thank you I thank all the participants for being with me for this discussion, a very short discussion on GCMS this afternoon. And possibly I would like to see all of you tomorrow afternoon also for a interesting discussion on a different analytical technique, atomic absorption spectrophotometry. And one of my colleagues also will be present tomorrow for a small discussion. And thank you once again. And in case if anybody wants to raise a question, we have some 10 minutes time before we end this program, because Vedika has told me that 5:30 we have to log out. So, but now it's only 5:10. We have got another 20 minutes, 15, 20 minutes left behind. So we can take few questions also. But if questions are too many, I will request Vedika to take down those questions and later on you can forward it to us. We will answer it and send it back to you. So that's also an option given to you. Okay. Over to Vedika.
Yeah. So we start with the question answer session. In our chat, we have few questions. Mr. Soham is asking, what is bleeding phenomenon that you discussed?
What is?
Bleeding phenomenon.
Bleeding phenomenon. Bleeding phenomenon. How is the person can identify himself?
Mr. Soham.
He is from which institute or from corporate?
No.
Oh, no, it doesn't matter. Doesn't matter.
Yeah.
Doesn't matter. No problem. See, when I say bleeding, means I am referring to the column. Any chromatography column, especially GC columns, can bleed. Bleeding is not in LC column. Bleeding is only in GC columns. What is the bleeding? The column contains stationary phase. And all these stationary phases, as I told you before, they are all chemical compounds. Different chemical compounds are used as stationary phases. And you are going to, during the course of the analysis, you are going to heat the sample. Any chemical compound which is used as a stationary phase has got a minimum temperature and a maximum temperature, and you are supposed to work within these two ranges. You are not supposed to cross the range. Okay, now for a certain column, suppose for example, if it is 280 is the maximum temperature, just a random example I'm giving, 280 degrees centigrade is the maximum temperature. Now by a user is going to use the column, say at 300 degree, well above 280. 280 is the cutoff, but he has increased the temperature. In that case, what will happen? The very, very small portions of the material, which is the stationary phase, which is a chemical material, will start degrading and it will come out of the column and go to the detector continuously. There's a continuous flow of small portions or small concentrations, small parts of the stationary phase is coming out continuously because you are going to a very high temperature because it is well above the limit of the column, and small amounts of continuously this material will come out. And then when it comes to a detector, the detector will sense it, but it is not stopping. It is continuously coming. So your baseline will always bend towards upper side. That means there will be a upper, the baseline should be actually flat. There should not be any change in the baseline. But whenever there is a bleeding, the baseline will start moving upwards. And that is basically because of bleeding. So bleeding is nothing but small portions of the stationary phase is coming out of the column because you have increased the temperature beyond its limit. That means your stationary phase is getting degraded. It is coming out in small quantity, going to the detector, and the detector is giving a response by way of continuous upward movement of the baseline. And this process is known as bleeding. That is why we are always advising the people never ever cross the maximum temperature what is recommended. If the recommended maximum temperature is 280, I will advise you not to cross 270, 10 degrees below that. Your column will be always stable, your column will not bleed, and your column life also will be enhanced. I hope I have answered the query.
Okay, sir. We go to the next question.
Yeah.
Ms. Nehalata is asking for plasma analysis. Which method is good, LCMS or GCMS?
Plasma analysis, exactly. Hemalata wants to find out what in plasma. She wants to find out plasma is a common. Plasma is a totally biological material. In plasma, what she wants to find out. That is more important. That will be a more relevant query.
Monish, can we unmute Snehalata madam? She is online.
Yeah. What does she want to find out in plasma? Is it a bioanalytical application?
Yeah, bioanalytical application.
Is a bioanalytical application. You must be trying to find certain drugs, small quantities of drugs in plasma.
Yeah, drug substance present in plasma.
So normally, most of the time, an LCMS is preferred, Hemalata, not GCMS.
Yes.
Yeah, for bioanalytical applications like serum and plasma, we use more of LCMS rather than GCMS.
Yes.
Yeah, I hope it's very clear. That is why when you go to any laboratory who is carrying out bioanalytical applications, you will find more number of LCMS. You may not find the GCMS there, but LCMS is a more appropriate equipment to do that.
Why so it is? Why it is so like that?
Many of the drug samples are totally non-volatile or highly polar for the GC column to take up.
Yes. Okay.
So it is very easy for you to analyze by LC column and detection by MS. So LCMS becomes very handy for you.
Yeah. Okay, sir. Thank
you. Yeah.
Okay. The next question is from Buddhi Prakash Kashyap. He's from Lucknow and he's asking what is the difference between retention time and retention index?
Okay. Retention time is the time at which the compound is coming out of the column and coming to the detector and getting detector. That's the retention time. Okay. Now retention time is always condition dependent. I change the column temperature, my retention time will change. I change the flow rate of my carrier gas, my retention time will change. I change my carrier gas, my retention time may change. So retention time is depending on the conditions. So you have to specify the retention time of this particular compound is so and so minute under so and so conditions. Because the moment I change the condition, my retention time is also going to change. Whereas retention index of a compound is the measure of a certain stationary phase to hold the sample, and it will not change with condition. Whether you use 100 degree for the column or you use 200 degree for the column, the retention index on that particular sample will be same, because it is only the measure of what is the retention capacity of that particular stationary phase for the given sample. It is not condition dependent. So under various conditions also, the same column will give the same retention index for a compound, whereas the retention times can be different. So retention index will change only if you change the stationary phase. So retention index of a compound, chemical compound, will always remain same on a given stationary phase, and will never change with conditions. So that is the retention index becomes a much more authentic way of identifying a compound rather than trying to identify the compound based on retention time. Sometimes retention time can change, so it can give some erroneous result. But if you go by retention index, we will never make a mistake. It can be an authentic way of identifying a compound.
Okay. Anybody else? If they have a question, kindly raise your hand so that we can unmute you.
There's a question on YouTube session, ma'am, from Indranil Davde. That is how analysis of azeotropic mixture is done, and can it be done with the GCMS?
Azeotropic mixtures. Azeotropic mixture of what? What are the components present in that?
He has not mentioned that exactly.
He has not mentioned. It all depends upon the components in that. I mean, azeotropic mixtures now, you know, when they are boiling also, many of the times they can boil together. But here, depending upon the polarity, we can adjust the polarity in such a way that again, finally, it depends on what are the compounds he is looking for. So that information we have to get. Then we can decide whether GCMS can be used or cannot be used.
Okay. And there is one more question. Why silica is not used as a stationary phase in GC?
Silica is not used as a stationary phase in GC. It is used as a stationary phase in GC, but only in GSC technique. Gas solid chromatography technique, it is used. Many times we can use silica, we can use graphitase carbon, we can use styrene divinyl benzene copolymer, we can use carbon molecular sieve. We can use different complexes. I mean, they are all, even silica can be used and alumina can be used, but they are all used only for gas separations. They are all in GSC technique, gas solid chromatography technique, but they are not used in normal GLC technique. GLC technique, we are going to use a organic liquid as the stationary phase. So it can be used in GC, but the type of column is different.
Okay. And for that azeotropic mixture, he had mentioned now it is ethanol and petrol. For example, that is ethanol and petrol.
Ethanol and petrol. See, petrol, when I say petrol, it contains different hydrocarbons. Okay. So the moment I introduce the sample, everything will come out of the column. But petrol is not a single compound. There may be different hydrocarbons that are present in petrol. Different carbon number hydrocarbons are present in petrol. So we need to critically see how the ethanol peak is going to get separated. We need to find out a suitable phase for that. Possibly we may have to use a longer column. And also I assume for a petrol, because most of the hydrocarbons can be non-volatile hydrocarbons, non-polar hydrocarbons. And my gut feeling is we can use a non-polar column for the separation. Because most of the hydrocarbons in this will be, but we will require a lot of optimization because plenty of peaks will come from ethanol, from petrol. And ethanol also being a volatile solvent, that also is going to come out. But we need to optimize the separation. But I think it can be done using a non-polar column in GC or GCMS.
Okay, and the last one question from the YouTube session, that is how to decrease the tailing problem.
I didn't get how to decrease
the tailing problem.
Acha, the tailing problem. Okay. See, tailing is a universal phenomenon. It's an accepted phenomenon in chromatography. Tailing you observe in GC, tailing you observe in LC also. Now, in the case of GC, tailing can be taken care of either by changing the temperature profile. We can normally change the temperature profile by changing the ramping, that is the rate of heating of the column we can change. And sometimes we can, in the case of LC, we can reduce the tailing by addition of certain small compounds like triethanolamine and very, very small concentration to the mobile phase. That is called a mobile phase modifier. So, and sometimes after doing all this, the tailing is not coming as a not getting reduced, then probably you may have to even think of changing the phase itself. So there are certain ways by which we can try to reduce the tailing. First of all, why tailing is coming, the sample is coming out of the stationary phase in a very reluctant manner. It is coming out very slowly. That means it is getting absorbed. Many times we can give some surface treatment on the sample. A surface treatment on the stationary phase that also will reduce the tailing. Because why? Active sites are available on the stationary phase, and many times these active sites are actually leading to tailing. That's basically ultimately they're getting resulted in tailing. The sample is getting absorbed for a prolonged period of time. There are certain treatments like TMCS treatment, HMDS treatment. These treatments are given to the stationary phase so that the stationary phase surface becomes totally inert and free of any absorbing sites, and thereby we can considerably reduce the tailing. I mean, there are different methods. This is one way. Then we can change the ramping, the temperature range, the ramping rates we can change. In the case of LC, we can modify the mobile phase composition. We can add small amounts of mobile phase modifiers. There are different ways by which we can reduce the tailing. But there is some little bit of tailing is always accepted, because as per USP also, there is a limit up to which tailing is accepted. And beyond that, it is not accepted. So if you look at some of the monograms also, USP, I mean, something like, say, for example, if I remember correctly, 1.2 tailing, 1.2 up to 1.2 is accepted by USP. And beyond that, it is not accepted. So tailing is an accepted phenomenon. It's happening in GC columns. It can happen in LC columns also. To a certain extent, it is accepted, but beyond that, it is not accepted. Because if too much of tailing comes, your quantitative analysis and also resolution will be affected. And that's the reason why too much of tailing is not advisable and not acceptable.
Okay. The last question for the session is now. People want to know which are the software that are used in data processing in GCMS.
GCMS, we have got our we have different GCMS solution software is there. For GC, we have lab solution software is there. Different softwares are there, and from manufacturer to manufacturer, these softwares
yeah, I think they vary. Yeah,
they can vary. Shimatsu will have their own software. A different company will have their own software. So from company to company, these softwares can be different. Shimatsu offers, for example, GC, we offer a lab solution software, and GCMS, we have a GCMS solution software, and different company will offer a different software. So it can depend upon the manufacturer.
I think we have covered most of the questions that participants have asked during the session.
Yeah.
We come to the end of the session now.
Yeah.
I think Sir has very widely explained and very lucidly explained the basics of GCMS so that the students can understand the topic and also simply blended it with industry perspective and requirement. Sir has very well put light on various applications of GCMS analysis in various industries, right from perfumery, fertilizers, food, biomedicals to pharmaceutical industry, including a very current ones like quantification of nitrosamines by GCMS HS. Sir has also asked us to follow 4 S values, that is sensitivity, selectivity, speed, and solution. Sir, I feel this can be applied to many other operations that we perform regularly for better outcomes in our life. Thank you so much, sir, for your wonderful technical talk.
It's my pleasure, and I thank all the participants. And I hope to see all of you tomorrow afternoon for another interesting discussion on atomic absorption.
I would request all the participants to kindly upgrade your Zoom version. Today many of you couldn't log in because of this issue, I think. Kindly please log in with the current new version of Zoom. We will also give you the YouTube link tomorrow like we did today. Thank you so much.
And Vendika, I think you have already given the link for tomorrow's session. Can I use the same link? I can use the same link tomorrow, no?
Yes, the link for day 2 is different than from day 1. Kindly use the link for day 2, which I sent on mail.
Okay. Thank you so much. Thank you so much.
Thank you all the participants. Hope to see you tomorrow.
Okay, I'm logging
The
out.
feedback,
Okay, all the best.
the feedback link will be sent to you by mail.
Okay.
Yeah. Thank you.
Thank you so much. Thank you all the participants. Once again, I'm logging out. Okay.
Okay. Yes. Thank you.